So there's another rule involving our laws of exponents, and that's the quotient rule. And we can think of it, again, just sort of intuitively. If I have x to the fifth divided by x to the third, and go back to what this power means. It means we're repeat multiplying x's 5 times. Little dots in between there to indicate multiplication. And x to the third means we're multiplying 3 x's together. And if I cancel, and think about if I cancel a number divided by itself, it cancels out to 1. The same with x's. An x divided by an x will cancel out to 1. An x divided by an x will cancel out to another 1. And I have one more here that I can do. All 3 of these x's on the bottom canceled out with 3 x's on the top, leaving me with x times x, or x squared on top. So you can think of it as subtracting, really, whereas multiplying like bases, we added. When we divide, we subtract. But let's go even further with that. If I have x to the 3 on top and x to the 5 on the bottom, and again, you're going to get to the point where you're not going to write all of this out, but this means I have 3 of those x's on top. I have 5 of those x's on the bottom being multiplied together. And again, if I think about x divided by x, that's going to cancel out to 1. There goes another one. There goes another one. All right, so it's 1 on top, because they all canceled out, over, and then I still have 2 x's on the bottom. And again, you can kind of look at this intuitively. Well, if I have 3 x's on top but I have 5 on the bottom, I'm going to have more on the bottom when I get done canceling. All right. The key is, though, to have it so that our exponents are positive before we do this idea of canceling. For example, if I have x to the negative 3 on top over x to the 5 on the bottom, I can't write down a deficit of 3 x's on top. And it's not 3 x's on top, because that would be x to the third. This is x to the negative 3. So what I'm going to do is use our property that says, well, if I have a negative exponent in the numerator, I can cross the line and change the sign of the exponent in the denominator. So this becomes x to the positive 3 in the denominator. X to the 5 is going to be left where it is because its power is already positive. And then I have 1 on top. Okay. So I have 1 over. And now think about it this way. The x's are on the same side. I have 3 x's, and then I have 5 more x's. 2, 3, 4, 5, all being multiplied together, which leaves me with 8 of them on the bottom. Okay. So let's try another one of those. What if I have x to the negative 5 on top, x to the negative 3 on the bottom? Well, again, the only way that this really works is if you have positive exponents that you can write down and think about. So I'm going to move x to the minus 5 down below the line, and when you cross the line, you change the sign of the exponent only. X to the minus 3, it's negative in the denominator. If I cross the line, I change the sign of it in the exponent. And then it goes back to what we did up here at this problem. I have 3 x's across the top, I have 5 across the bottom. So if I cancel an x for an x out, I'm going to be left with 2 of them on the bottom, or in your denominator. All right. Let's bump it up even further and try a problem like this. If I have x to the third, y to the negative 2 on top, divided by y to the fifth, and we're going to raise that to the negative 4th power. There's multiple ways you can do these problems. I like to get rid of the outside exponent first, but that's just me. You could simplify inside here first and then get rid of the outside power. In any case, we want our final answer to have positive exponents only. So if I raise everything inside to the outside power, I have to use the property that allows me to do that, and that's I multiply the powers together. When you raise a power to a power, you multiply. So this is going to be x to the negative 12, y to the positive 8, negative times negative, divided by y to the negative 20. My next step would be to get rid of negative exponents and then count up and see what I have left. So the x to the minus 12, that whole term right there is going to drop down and become x to the positive 12. Y to the minus 20 has a negative in its exponent, so I'm going to cross the line, change the sign. The y to the 8th is going to stay put. It's all multiplication here. It's a positive exponent, by the way, so that's why it's staying where it is. And now go ahead and think about if I have 8 y's and then I have 20 more y's. I'm not going to write all that out, but I end up with a total of 28 y's on top, and on the bottom, my x to the 12th. Now I can't simplify any further because there's no canceling going on. These are different bases, so I can't cancel like I was doing up here when I have the same base. This would be my final answer. Okay, let's try another. If I have a negative 3 times x to the 5th, y to the minus 4, raised to the negative 3 power. And again, I like to take care of the outside power first, but notice this time the negative 3 power is only responsible for this base here, not the number negative 3. The negative 3 is just hanging out in front. I'm raising the x to the 5th to the negative 3 power, so again, multiplying. Y to the negative 4 raised to the negative 3, so again, multiplying the powers together. And then simplifying anything with a negative exponent. So just imagine that there's that little division bar there. I'm going to cross the line, change the sign, but negative 3 has a power of 1. It's not showing it's 1. Its exponent is positive. I know the number is negative, but I said negative exponents cross the line and change their signs. So the negative 3 stays in the numerator. The x to the minus 15 will drop below the line and change its power to positive 15, and then y to the 12 stays put. And that would be your final answer. Again, there's no canceling. You don't have the same variable top and bottom, so I can't cancel any further than that.